There is a place on the moon that has not seen sunlight in 2 billion years. Not a shadow, not a cloud passing over, not the temporary dark of a lunar night, a permanent, total, unbroken absence of light, maintained by geometry, by the tilt of an axis, by the physics of how this world rotates around a distant star it can no longer fully face. The temperature there is negative 186 degrees Celsius. It has been that cold, without variation, without relief, for longer than complex life has existed on Earth. At the bottom of a crater called Shackleton, at the exact south pole of the moon, something has been accumulating in that cold and that dark for 2 billion years. Slowly, molecule by molecule, comet by comet, a substance that began its journey in the outer solar system, inside the frozen bodies of ancient impactors, and ended it here, locked into the dust, preserved in a silence so complete that no instrument we have ever built can fully describe it. That substance is water. And tonight you are going to stand inside the crater where it waits. Before you get there, you will cross the rim of the largest confirmed impact structure in the entire solar system. You will stand on the edge of a world that has not changed its surface in 3.5 billion years. You will look up at an Earth that does not move in your sky, a pale blue-white arc, fixed at one angle, one position, never rising, never setting. You will feel the ground beneath your boots and understand that the dust there, the fine gray powder that your suit displaces with each step, is older than almost anything else in the known universe. And then you will step off the rim and begin your descent into the dark, into the longest running cold trap in the solar system, into a place where the ice remembers where it came from. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Every detail in this story comes from real scientific research and observation. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. The moon's south pole is not a place that announces itself. There is no dramatic feature visible from Earth that marks it, no ring of mountains glowing in a special color, no crater whose name everyone knows the way they know the Sea of Tranquility, or the face of the crescent moon on a clear night. From Earth, the South Pole region is a gray cratered blur near the limb, the edge where the moon's face curves away from us. You can barely resolve it with a backyard telescope. The geometry of our view from Earth means the South Pole is always tilted away, always compressed, always seen from an angle that flattens its dramatic topography into a crumpled horizon. And yet it is one of the most scientifically significant locations in the entire solar system. The reason is tilt. Earth's axis is tilted 23.5 degrees relative to the plane of its orbit around the sun. That tilt is what gives us seasons. The reason July is warm in the northern hemisphere and cold in the southern. The reason the Arctic receives the midnight sun and the Antarctic endures months of polar night. That tilt is dramatic. It moves the climate of an entire planet. The moon's axis is tilted 1.5 degrees. 1.5 degrees relative to the plane of its orbit. Almost perfectly vertical, almost perfectly upright. The consequence of that near zero tilt is extraordinary. At the poles of the moon, the sun does not rise and set the way it does on Earth, or the way it does in the equatorial regions of the moon itself, where every spot on the surface swings from 2 weeks of blazing sunlight to 2 weeks of complete darkness. At the lunar poles, the sun never climbs high above the horizon. It circles the horizon all year long, skimming across it, rising perhaps 1.5 degrees above it at most, never arcing overhead, never flooding the landscape with vertical light the way it does near the equator. This means that the floors of craters near the lunar poles, craters deep enough and positioned correctly, never receive any direct sunlight at all. Not seasonally, not cyclically, not in any known time frame. Never. The physics of a 1.5 degree tilt, combined with the geometry of a 21-kilometer wide crater that is 4.2 kilometers deep, means that the sun's light, always arriving at a low angle, is physically blocked by the crater walls before it can ever reach the floor. The walls of Shackleton Crater rise more than 4 kilometers above its interior floor, and the sun's maximum elevation angle at that latitude is less than 2 degrees. The math eliminates the possibility of sunlight reaching the interior entirely. And the crater has been in this orientation, on the axis of the moon's rotation, for approximately 2 billion years. 2 billion years of absolute darkness. 2 billion years of cold accumulating, stabilizing, deepening, holding. The floor of Shackleton Crater maintains an average temperature of about 87 Kelvin, that is negative 186 degrees Celsius, colder than liquid nitrogen, colder than almost any naturally occurring environment anywhere in the inner solar system. There is no wind on the moon to distribute that cold. There is no atmosphere to carry heat from sunlit regions to shadowed ones. The thermal environment of the lunar surface is entirely governed by radiation, by sunlight absorbed and re-emitted as infrared heat, and in the places where sunlight never arrives, the surface simply radiates the last of its heat out into the vacuum of space and gets no energy back. It becomes a cold trap. The term is precise. A cold trap is a region so cold that certain volatile molecules, water, carbon dioxide, ammonia, methane, that land there cannot escape. On most of the lunar surface, water molecules that arrive from a comet, impact, or from chemical reactions in the regolith are quickly energized by sunlight. They hop, they bounce across the surface at short intervals, gaining and losing energy from each brief exposure to the solar radiation, eventually either escaping the moon's gravity entirely or being destroyed by ultraviolet light and solar wind. The average water molecule on a sunlit part of the moon survives a matter of days before it is either lost to space or chemically broken apart. But a molecule that hops its way into a cold trap does not hop back out. The temperature is too low. The molecule freezes onto the surface. It bonds into the regolith dust at a depth so cold that it cannot acquire enough thermal energy to sublimate, to transition directly from solid to gas, no matter how long it waits. It is sequestered, preserved, locked in. Over 2 billion years, with an irregular but continuous supply of water from comet and asteroid impacts, from solar wind interactions with oxygen-bearing minerals in the regolith, from the long-ago outgassing of lunar volcanoes. Over all of that time, water molecules have been hopping their way across the moon's surface, bouncing toward the poles and falling into the dark of craters like Shackleton. Molecule by molecule, year by year, ice accumulating in the longest-running freezer in the inner solar system. A NASA study published in October 2024, using data from the Lunar Reconnaissance Orbiter, found that ice deposits in permanently shadowed regions near the lunar South Pole are significantly more widespread than previously estimated, extending outward from the pole to at least 77 degrees south latitude, covering an area potentially equivalent to more than 40,000 square kilometers across both poles combined. For each square meter of surface sitting above a confirmed deposit, the study estimated at least 5 liters of ice within the top meter of regolith. 5 liters per square meter, across thousands of square kilometers, preserved in a cold that has been holding since before the first multicellular organisms appeared on Earth. Tonight, you are going there. You are standing on the rim of Shackleton Crater. The ground beneath your boots is loose, powdery regolith, lunar soil that has been processed by billions of years of micrometeorite impacts into something finer than talcum powder in places and rougher in others, where larger impacts have left sharp angular fragments of highland rock that have never been weathered by wind or water. Your boots press into it slightly with each step. The pressure registers through the soles of your suit. You feel the surface give just a little, then hold. It is quiet. Not the quiet of a forest at night, where there is still air moving between leaves, still the occasional call of an animal in the distance, still the low hum of a planet full of living things. This is the quiet of a world that has no atmosphere. Sound cannot propagate here. If a rock the size of your fist fell from the crater rim and struck the surface below you, you would not hear it. You would see a small puff of dust rising slowly and falling back in the moon's 1/6 gravity, silently, completely silently, and that would be the entire event. No crack, no echo, no impact sound of any kind. The vacuum here is among the most complete in the solar system. The lunar surface pressure is approximately 10 to the -10 torr, 100 trillion times less pressure than at sea level on Earth. In this environment, the mean free path of a gas molecule, the average distance a molecule travels before colliding with another, is measured in kilometers. The handful of gas atoms that do exist near the lunar surface form what is called an exosphere, rather than an atmosphere, a collection of individual molecules moving in ballistic arcs, barely interacting with each other, loosely bound to the surface by the moon's gravity. Sodium, potassium, argon, helium, trace quantities, quantities so small they would register as essentially nothing in any instrument designed for Earth. You breathe through your suit's life support system. Everything else here is silence. The sky above you is black. Not the deep blue black of a clear night sky from Earth, where the upper atmosphere still scatters a small amount of light and the horizon softens from black to purple. Here the sky is a true, perfect optical black. The stars are visible at all times, not just at night, because there is no atmospheric scattering to wash them out in daytime. If you looked toward the sun right now, you would need to shield your eyes or use your visor's darkest filter. The sun in the vacuum of space, with no atmosphere to diffuse or soften it, is a point of extraordinary intensity. But look away from the sun in any direction, and the stars are there, unblinking. No atmosphere to make them scintillate, no air movement to distort them. The Milky Way, if you face away from both the sun and the brightly lit crater rim, stretches across the black sky in its full, unobstructed arc. And fixed at approximately 19 degrees above the horizon, fixed, not moving, not rising or setting, just there, is Earth. Earth hangs in the sky here, the way the moon hangs in Earth's sky, except it does not move. Because the moon is tidally locked to Earth, one face always turned toward the planet, one face always turned away, a rotation period that exactly matches its orbital period. The Earth, as seen from a fixed point on the lunar surface, never rises and never sets. It moves slightly due to the moon's orbital eccentricity, an effect called libration that causes it to wobble a few degrees over the course of a month. But it does not cross the sky. It does not change its position in any dramatic sense. It simply stays, a pale blue sphere, visibly a sphere in a way that it never appears from the ground, covered in white cloud patterns that shift over the course of days, but whose position on the sky is constant. From the South Pole, Earth appears near the horizon. That 19-degree elevation means it hovers just above the jagged rim of the surrounding terrain, partially obscured by the high peaks that define the crater landscape. You can see it from where you are standing. It is blue, white, impossibly small from here, and yet visibly a world, visibly a place full of atmosphere and water and life, all of that packed into a sphere about 4 times the apparent diameter of the full moon as seen from Earth. The distance between you and it right now is approximately 384,000 kilometers. A radio signal takes 1.25 seconds to cross that distance. If you spoke, your voice would arrive on Earth 1.25 seconds later. Their reply would take another 1.25 seconds to return. Every conversation with Earth from where you are standing has that pause built into it, a 2.5-second gap that is not technical, not a network delay, but simply the physical distance between two worlds and the finite speed of electromagnetic radiation. You stand on the rim and look at Earth and let the scale of that settle. Then you look down. The interior of Shackleton Crater descends in front of you. The slope is steep, approximately 30 degrees, and uniform in a way that tells you this is a well-preserved impact structure, the crater walls not significantly eroded by subsequent impacts or any geological process. The floor is approximately 4.2 kilometers below the rim where you are standing. In the 1/6 gravity of the moon, 4.2 kilometers of vertical descent would feel different than on Earth. Your weight, reduced by 83%, means that the physical effort of descending that slope would require far less muscular exertion than the same slope on Earth. But the psychological fact of it, the knowledge of how much lower that floor is than where you stand, does not diminish with reduced gravity. The floor of this crater is deeper below you than the height at which commercial aircraft cruise above Earth's surface. And it is dark down there. Not fully dark, not yet from your position on the rim, where the sun at its low angle still catches the upper portions of the crater walls and reflects some light downward. But the floor is dark. The light that reaches it is indirect, reflected, scattered, not enough to cast a shadow, not enough to see color, barely enough to distinguish the outlines of the terrain. The ShadowCam instrument aboard the Korean spacecraft Danuri was built with a sensor 200 times more sensitive than previous lunar cameras, specifically for the purpose of imaging these permanently shadowed regions. Its photographs of Shackleton's interior show a dim gray landscape, boulders, the ridgeline of a central peak, a faint texture to the floor that suggests regolith compacted differently than the sunlit highlands above. That faint texture, that different compaction, that anomalous reflectivity, those are in part the signatures of the ice. Not blocks of ice visible to the eye, not a frozen lake. The ice here is mixed into the regolith, locked into the gaps between dust particles, coating the surfaces of fine-grained mineral fragments at a microscopic scale. The concentration varies. In the coldest, most protected zones near the center of the floor, Estimates suggest the near-surface material could be as much as 20% water by mass in some localized deposits. In wider areas, the concentration is lower, a few percent, 10 parts per million in some regions, scattered and patchy in ways that reflect the uneven history of how the molecules arrived and settled. But it is there. Confirmed by neutron spectrometers that detect the hydrogen signature of water. Confirmed by the ultraviolet albedo measurements that show surfaces more reflective than bare regolith could account for. Confirmed by the impact of the L-Cross spacecraft in 2009, which deliberately crashed into the nearby crater Cabeus and generated a plume that was analyzed in real time by a following spacecraft. Water vapor, pure water ice crystals, detected unambiguously in the ejecta cloud, roughly 100 kilograms of water vapor released in a single impact, floating above the crater floor before dispersing into the vacuum. 100 kilograms of ancient water, freed from the regolith by a planned collision, briefly visible to instruments before returning to the cold and the dark. You begin your descent. The slope is gray beneath your boots. The regolith here on the sunlit crater wall is the same as everywhere else on the lunar highlands, a mixture of crushed feldspar and pyroxene, the dominant minerals of the ancient highland crust, processed by impact after impact into a range of particle sizes from sharp millimeter-scale fragments to the finest submicron dust. Your boots press into it. Each step kicks up a small, slow arc of dust particles that rise briefly in the 1/6 gravity and then settle back, always settling back, because there is no air to carry them sideways, no turbulence to mix them, just the moon's gravity pulling each particle back to the surface in the same slow arc. The slope is approximately 30 degrees. You descend carefully. The terrain is not uniform. There are boulders, ejected from the crater wall during smaller subsequent impacts, ranging in size from a few centimeters to several meters across. Some of them have sat in exactly the same position for hundreds of millions of years. In the absence of weathering, in the absence of water and wind and thermal cycling, significant enough to move them, they simply rest where they landed. The regolith around their bases is undisturbed. The dust that has slowly accumulated around them by micrometeorite gardening, the slow churning of the top few centimeters of lunar soil by the constant rain of tiny impactors, has built up over time in ways that reflect exactly how long each boulder has been sitting in that position. Some of these boulders are older than any rock on the surface of Earth. The highland crust here dates back to the period of crustal solidification following the moon's formation, the final stages of cooling of what is called the lunar magma ocean, the period between roughly 4.5 and 4.3 billion years ago, when the entire moon was covered in a global ocean of molten rock. As that ocean cooled and crystallized, lighter minerals like plagioclase feldspar rose to the surface and formed the bright highland crust. Heavier minerals like olivine and pyroxene sank toward the interior. The rock you are walking on, or rock compositionally identical to it, has been on the surface of the moon in roughly the same form since approximately 4.4 billion years ago. It is older by more than 1 billion years than any rock found anywhere on the surface of Earth. The walls of the crater are composed of this ancient highland material, anorthosite, a rock type made almost entirely of plagioclase feldspar, pale and bright, catching the indirect light and reflecting it downward into the dark of the crater floor in a faint diffuse glow. This reflected light is what allows even the most sensitive instruments to image the interior, albedo from the walls, not sunlight, just the moonlight equivalent of earthshine, light reflected off one surface and illuminating another that cannot be reached directly. You are descending into a place illuminated only by indirect reflection, by ancient rock catching old light and redirecting it downward into the permanent dark below. The temperature drops as you descend. Not dramatically, not the way temperature drops as you descend into a cold cellar on Earth, where the air carries the chill and wraps around you. There is no air here, so there is no convective cooling, no wind chill, no thermal contact with the environment through a moving medium. The temperature change you would experience is radiative, the warming effect of direct solar radiation on your suit's outer surface diminishes as you descend below the crater rim, and the sun's direct line of sight is blocked by the crater wall above you. Above the rim, sunlit, your suit's outer surface is exposed to a solar flux of approximately 1,360 watts per square meter, the same solar constant that illuminates the top of Earth's atmosphere, undimmed by any intervening medium. That radiative energy heats the outer surface of your suit significantly. Below the rim, shaded, that heating disappears abruptly, and the only energy inputs to your suit's surface are the faint reflected light from the crater walls and the infrared radiation emitted by the regolith around you, both of them very low energy inputs compared to direct sunlight. The floor of the crater, which receives none of these inputs directly, has stabilized at 87 Kelvin. That is the equilibrium temperature of a surface that has been absorbing no energy for 2 billion years. You continue down. The light fades slowly as the crater walls rise around you. The direct view of Earth is lost as the rim closes over. The sky above narrows from a broad arc to a strip to a slot. The stars are still visible in that slot. The black of space is the same at the bottom of a crater as it is at the top, but the field of view tightens and the sense of enclosure increases. This is one of the most isolated locations in the inner solar system. Not distant from Earth in the way that the outer planets are distant, not hundreds of millions of kilometers, not years of travel time. The moon is close, 384,000 kilometers, a 3-day journey, and yet the floor of this crater, at this moment, shares more environmental characteristics with the deep outer solar system than it does with the sunlit surface of the moon 2 kilometers above you. The temperature is close to what you would find in the Kuiper Belt. The ice chemistry is chemically similar to what you would find in a comet nucleus. The extreme cold and the vacuum and the absence of any energetic radiation reaching the surface make this place a preserved record of the earliest chemistry of the solar system, a chemical archive that has been held in stasis for longer than the Cambrian explosion has been over. The floor is approaching. The slope levels out gradually. The terrain softens from the steep crater wall angle to a more gradual transition zone, and then to the floor itself, a surface that no instrument has directly sampled and no human has ever touched. The floor of Shackleton Crater is measured and mapped by orbital data, by laser altimetry from the Lunar Reconnaissance Orbiter's LOLA instrument, which has characterized the topography of the lunar surface down to a resolution of about 20 meters, and by radar instruments that can see below the top layer of regolith and detect the scattering properties of subsurface materials. From that orbital data, scientists know that the floor is not flat. There is a central mound, a feature typical of simple impact craters of this size, a rebound structure formed in the moments after the impactor struck, and the crustal rock briefly behaved like a fluid. The central mound rises perhaps 200 meters above the surrounding floor. The floor itself is uneven, with a texture that suggests a mix of undisturbed ancient regolith and areas reworked by the slow, ongoing process of micrometeorite gardening and occasional small impactors that have struck even this deeply shadowed floor in the billions of years since the crater formed. Some of those small craters within the floor of Shackleton have exposed subsurface material. Some of them may have excavated pockets of ice-bearing regolith and redeposited the material on the surface, mixing it with the surroundings. A 2026 study in the journal NPJ Space Exploration estimated that approximately 74% of the permanently shadowed regions near the South Pole have not been significantly disturbed by impacts, meaning the ice in those regions has remained essentially undisturbed since it was deposited. 26% may have been rearranged, redistributed, but not destroyed. The cold trap preserves what enters it. You step onto the floor. The regolith here is finer than on the rim, not uniformly. There are still small rocks, still angular fragments of highland material that have arrived over the millennia from impacts on the crater walls above, raining slowly down into the permanent shadow. But the general texture is finer, and the way your boots press into it feels different. Slightly more compressible, slightly less resistant. You kneel slowly. The motion is easy in the low gravity. Your suit's life support system continues to hum, the only sound in your immediate environment, the mechanical purr of the systems keeping you alive in a place where nothing can live unaided. You look at the surface directly in front of you. In the faint reflected light from the crater walls, the regolith looks the same as it does everywhere else on the moon: gray, powdery on the surface, slightly coarser where angular fragments protrude. No visible shimmer of ice, no frost crystals, no white patches. But the ice is there. Not on the surface. Most models suggest that the very top layer of regolith, even in permanently shadowed regions, has been thoroughly processed by micrometeorite impacts and solar wind particle bombardment over billions of years, producing a mixed garden zone where the ice concentration is lower than in the more protected subsurface layers. The richest deposits are expected to begin perhaps a meter or two below the surface, in regions where the gardening process has not reached, where the cold trap has been continuously holding for the full 2 billion years without disturbance. A meter below your knees, possibly less, the ice waits in the regolith, mixed into the dust, coating the mineral grains, filling the tiny pore spaces between particles with something that arrived here from the outer solar system, water that formed in a molecular cloud that was incorporated into a comet nucleus 4.5 billion years ago, that traveled through the inner solar system, struck the moon in some ancient impact, and was hopped molecule by molecule across the surface over millions of years until it settled into this cold and stayed. The same water chemically, altered slightly by cosmic radiation over the long journey, incorporating traces of other molecules that have arrived in the same way: carbon dioxide, methane, ammonia, the chemical signatures of the outer solar system, preserved alongside the water in the cold trap chemistry of the floor. You are kneeling over an archive. Not a library, not a collection built deliberately, a natural accumulation of the chemistry of the early solar system, preserved by physics, by tilt, by the accident of a crater forming in exactly the right place on a world with almost no axial tilt. The ice in this crater is older than any ocean on Earth. It was here before the first organisms learned to photosynthesize, before the first multicellular life emerged in the Precambrian seas, before the Cambrian explosion that produced the blueprints for almost every animal body plan alive today, before the dinosaurs, before the mammals, before the hominids, before the first humans looked up at the moon and wondered what it was made of. All of that time, the cold held. The ice stayed. You stay kneeling for a moment in the silence of the crater floor, in the faint gray-lit dimness of the most isolated cold environment in the inner solar system, in a place that no human being has ever stood and no human being has ever reached, and which has been preserved in exactly this condition for longer than complex life has existed anywhere we know of. The silence around you is complete. Your suit's systems hum. Earth is somewhere above the crater rim, invisible from where you are now, fixed in the sky you cannot see. The ice waits beneath you, and you breathe. In, out. The floor of Shackleton Crater extends in every direction around you, a roughly circular space 6.6 kilometers across at its widest point, enclosed by crater walls that rise to more than 4 kilometers on all sides. In the permanent shadow, without the reference of sunlight to define direction, orientation is different. There is no east or west defined by a rising or setting sun. The compass directions exist in principle. The lunar South Pole is directly overhead in terms of the rotational axis, and the crater's position means that the pole itself passes through the rim, not the floor, but the felt sense of direction that humans use instinctively on Earth, organized around sunlight and sky and the movement of light across the landscape, is absent here. Direction here is defined by topography. The crater walls rising around you, the central mound, visible in the faint reflected light as a raised mass toward the center of the floor, the uneven texture of the ground beneath your boots. These are your references. This is how you navigate. You stand and begin to walk slowly toward the central mound. The moon's gravity, 1.62 meters per second squared, compared to Earth's 9.8, means that each step takes longer than it would on Earth. Your body rises slightly with each footfall and settles slowly, and the gait that human beings naturally develop on the lunar surface is something between a walk and a series of controlled hops, a rhythm that takes advantage of the low gravity rather than fighting it, allowing each stride to cover more ground with less muscular effort. The Apollo astronauts, working in suits less advanced than anything you are wearing now, intuitively settled into this gait after only a few minutes on the surface. You settle into it now. Each step is slow. Each step is deliberate. Each step displaces a small amount of regolith that rises in a slow arc and settles back exactly where physics dictates, in no atmosphere to complicate the trajectory, following a perfect ballistic arc in the moon's gravity. The central mound grows closer. It is a feature formed 3.6 billion years ago, in the first second of the crater's existence, in the moment of the original impact, a body perhaps 1 to 2 kilometers in diameter, striking at somewhere between 10 and 20 kilometers per second. The energy released was enormous. The impactor was vaporized. The target rock was melted, compressed, ejected in all directions. And then, in the seconds after the impact, the crater floor rebounded. The crustal rock, briefly behaving plastically under the enormous pressure of the impact, bounced back upward in a central rebound, a structure that is common in simple craters of this size, analogous to the drop-splash pattern you see when a droplet falls into water and a central column briefly rises in response. That rebound froze in place as the rock solidified. The central mound you are walking toward is that frozen rebound, 3.6 billion years old. Not moved, not eroded, not altered by any geological process since the moment it formed. The moon has no plate tectonics, no volcanic activity currently occurring, no liquid water to carve into it, no wind to erode it. The only modification to this structure since it formed has been the slow sandblasting of micrometeorite impacts. Billions of years of tiny impactors striking the surface at high velocity and gradually processing the top layer of rock into regolith. But the structure itself, the geometry of it, the height and shape of it, is essentially as it was on the day the crater formed. You walk toward ancient rock that has not been touched by sunlight in 2 billion years. The temperature around you is holding at approximately -186 degrees Celsius. Your suit is maintaining internal temperature at approximately 20 degrees, a comfortable, habitable interior in a place where without the suit, exposed tissue would freeze solid in seconds. The thermal management system in your suit is working continuously, drawing away the metabolic heat you generate and either storing it, radiating it, or managing it through the suit's systems. You are a warm organism inside a machine designed specifically to keep you warm and alive in one of the coldest natural environments reachable within the inner solar system. The thought is not abstract. You feel the hum of those systems. You feel the slight pressure of the suit against your body. You are aware, at a low but continuous level, that the interface between your survivability and the environment around you is your suit's integrity, a material boundary between the habitable and the uninhabitable. This is not fear, it is awareness. The same awareness that any careful scientist or explorer carries in a difficult environment. The knowledge of where you are and what keeps you there. The moon, in this moment, is not threatening you. It is simply the moon, a world following the laws of physics as it always has. Indifferent not from hostility, but from the simple fact that indifference is the natural state of a world that formed without life and has never had to account for it. The south pole of the moon is not hostile. It is just cold and quiet and old. You reach the base of the central mound and look up its slope. It rises roughly 200 meters from the surrounding floor. In the faint reflected light from the walls, you can make out the rougher texture of the mound's surface. More angular fragments here, less of the fine powdery texture of the surrounding floor. The impact that formed this structure exposed deeper crustal material, and the composition of the mound reflects that. More anorthosite, more of the ancient highland crust that formed in the earliest period of lunar history. The rock that carries within it the chemical signatures of the lunar magma ocean and the conditions of the moon's formation. You sit at the base of the mound. The ground is cold, not felt through your suit. The thermal insulation prevents that, but known, present as fact in the data your suit's sensors provide. Cold in a way that has been continuous, unbroken, steady for 2 billion years. You look up. Through the narrow slot of sky above the crater, the stars are visible. The same stars that are visible from the crater rim, from the sunlit highlands above, from the far side of the moon, from Earth. The same stars, but seen from a different geometry, from inside a 4-kilometer deep bowl of ancient rock, on the floor of a cold trap that has been accumulating the chemistry of the early solar system since before complex life existed. The light from those stars takes years to reach here. The nearest star system, Alpha Centauri, is approximately 4.2 light-years distant, meaning the light currently entering your visor from those stars left their surface 4.2 years ago, traveling at 300,000 kilometers per second through the vacuum of space, and arrived here at this specific place on the floor of a lunar crater. The light from more distant stars left centuries or millennia ago. The light from the brightest galaxies visible to the naked eye from the moon left millions of years ago. The universe is not silent in terms of what it is sending, but you hear none of it. You are on the floor of a cold trap on the moon, in a vacuum, in a world without air to carry any signal that is not electromagnetic. What surrounds you, the stars, the ice beneath you, the ancient rock, communicates only in physics, only in the silent language of gravity and radiation and temperature. And that is enough. That is, in its own way, complete. The ice beneath you contains hydrogen atoms that formed in the cores of stars that no longer exist. The oxygen that bonds with that hydrogen to form water was forged in the same stellar cores, released in supernovae, incorporated into the molecular cloud that became the solar system, built into comets in the outer solar system, and eventually delivered here. The minerals in the regolith around you contain silicon and oxygen and aluminum and iron and calcium that have the same stellar origin, atoms assembled in stars across the history of the Milky Way, gathered into the proto-solar nebula 4.5 billion years ago, differentiated by chemistry and gravity into the rocky inner solar system, and then shaped by impact into this world, this crater, this floor. You are sitting at the bottom of the moon's oldest cold trap, and the materials around you have been traveling through the universe for most of the universe's history. They came to rest here. You breathe in the suit's recycled air. You breathe out. The suit cycles, the life support hums, the stars hold still above the rim. The ice holds still beneath you. The cold holds steady at negative 186 degrees Celsius. And the silence continues. Complete. Unbroken. As it has been for 2 billion years. You do not need to move. You do not need to do anything. You have arrived somewhere that almost nothing in the universe can reach, and you are resting inside its permanence, inside its cold and its dark and its stillness, and the silence around you is not empty. It is full of age. Sit with the quiet of the floor for a moment. Let the weight of the temperature and the dark settle around you. The crater walls rise on all sides, silent geometry, 4 kilometers of ancient highland rock holding the cold in place. Nothing moves on the crater floor. Nothing has moved here, not meaningfully, not at any scale that a human body would register, for 2 billion years. In, out. The world outside this crater is not entirely still. Above the rim, the sun circles the horizon, never setting, never rising high enough to reach you, but present, a constant low light on the peaks and ridges that define the crater's edge, the peaks of eternal light, named not as poetry, but as fact. Certain ridgelines near the lunar South Pole, specific high points on the rim of Shackleton and the surrounding crater complex, receive direct sunlight for more than 90% of the lunar year. Some of these peaks are illuminated for over 220 consecutive days before a brief period of shadow interrupts them. Peaks of eternal light. These ridgelines have been proposed as the logical location for a permanent human outpost at the lunar South Pole. The solar energy available there is sufficient to power a small station continuously. The communication line of sight to Earth is relatively clear from these elevated positions, and the distance from the permanently shadowed regions where the ice exists is manageable. A descent of a few kilometers into the crater below, or a traverse to nearby craters where ice deposits have also been identified. The geography of the lunar South Pole is in this respect a kind of gift. Solar power above, water below. The two requirements for sustained human presence, separated by a vertical distance of a few kilometers and the physics of a 1.5-degree axial tilt. This is not coincidence. It is the geometry of the moon, and it is real, and it is why the South Pole of the moon is the primary target for the next generation of human lunar missions. But from where you sit on the floor of Shackleton, the peaks above you are invisible. The rim is visible, the line where the crater wall meets the black sky, but the specific ridgelines of the peaks of eternal light are on the outer side of that rim, in sunlight you cannot see from here. Here there is only the cold, the dark, the ice, the age. You close your eyes inside your visor. The suit hums. The temperature holds. The crater holds everything in place, every grain of ice, every dust particle, every fragment of ancient highland rock, exactly as it has been holding them with extraordinary fidelity for 2 billion years. Nothing here is in a hurry. Nothing here needs to move. And slowly, in the deep quiet of the most ancient cold trap in the inner solar system, the pace of your thinking begins to match the pace of this place. Slower, quieter, held. The south pole of the moon is approximately 384,000 kilometers from where your body is right now, lying still in the dark of your room. The floor of Shackleton Crater is colder than any place your body has ever been or will ever go. The ice there formed before your planet had complex life, and none of it is going anywhere. The cold trap holds. The crater holds. The moon holds. Let the stillness of that reach you, not the cold. You are warm, you are in your room, your body is safe, but the stillness, the sense of a place so stable, so preserved, so unchanging, that the word ancient becomes inadequate to describe it. The word permanent becomes closer. The word forever is too absolute. Nothing lasts forever. But it is closer to the feeling of the floor of Shackleton Crater than most words available in human language. Let your body settle into stillness. Let your breathing slow to match a pace that has no urgency in it. The crater has been waiting 2 billion years. It does not mind waiting a little longer. The ice is there. The cold is there. And you are here, held gently in the dark, with the same universe surrounding you that surrounds the floor of Shackleton, the same stars overhead, the same physics at work, the same ancient atoms in the air you breathe. Let your weight settle into wherever you are resting. Let your hands be still. Let your eyes stay closed. The moon is out there tonight, on the other side of your window or your wall or your ceiling, fixed in its orbit, turning slowly through its cycle, its south pole tilted at 1.5 degrees toward the void. And in a crater at that south pole, in absolute darkness and absolute cold, 2 billion years of ice waits in the regolith, undisturbed, preserved, perfectly still. Let yourself rest in the stillness of something that old. Let sleep find you in the quiet of a world that has been resting for longer than you can fully understand. The cold holds, the dark holds, and slowly, you are held too. The cold does not move. That is the first thing to understand about this place. From a scientific standpoint, if you have been sitting here long enough to begin thinking clearly again, the cold of the floor of Shackleton Crater is not cold in the way that a winter night is cold, where the temperature changes as the clouds shift, or the wind picks up, or the hours move toward dawn. This cold is structural. It is the equilibrium state of a surface that has been absorbing no energy from direct sunlight for 2 billion years. It is not a temperature the crater is moving through. It is the temperature the crater has arrived at and stayed. 87 Kelvin, negative 186 degrees Celsius. A temperature so low that the thermal motion of molecules in the regolith around you is reduced to a fraction of what it would be at Earth's surface. Thermal motion is what allows atoms and molecules to behave like a gas, to escape a surface, to react with other molecules. At 87 Kelvin, that motion is so suppressed that even molecules that would normally be gases at room temperature, carbon dioxide, ammonia, methane, and most critically water, cannot acquire enough energy to transition from the solid phase, locked into the regolith, and escape into the vacuum above. This is why the ice has stayed. Not because of a container, not because of any physical barrier trapping it in place, but because the thermodynamics of this environment make departure energetically impossible. The escape rate of a water molecule from a surface is a function of its temperature. At 87 Kelvin, the escape rate from ice-bearing regolith is essentially zero over any humanly comprehensible time period. A water molecule frozen into the regolith here 2 billion years ago is still frozen into the regolith here now. Its position has not changed measurably. Its chemical identity has not changed. It is still water, still H2O, though perhaps with minor radiation-induced modifications at the molecular level from the long exposure to cosmic rays and solar wind particles that can penetrate a meter or so into the regolith, even in permanently shadowed regions. But the molecule is here. 2 billion years and it has not moved. The ice in the regolith around you right now is not a single deposit in the way that a glacier is a single deposit, a continuous body of ice with defined boundaries. It is distributed, dispersed through the regolith in varying concentrations, filling the pore spaces between mineral grains, coating the surfaces of dust particles, concentrated most heavily in the zones where the cold is most extreme, and the delivery of water molecules has been most consistent over geological time. The concentration varies with depth. The very top layer of the regolith, the upper few centimeters, has been continuously processed by a phenomenon called impact gardening. The moon's surface, in the absence of any atmospheric protection, is constantly struck by micrometeorites, tiny particles mostly smaller than a millimeter, arriving at high velocity from all directions. Each impact is individually small, but over billions of years, the cumulative effect is significant. The top layer of the regolith has been churned, mixed, overturned, and remixed to a depth of roughly 2 meters by this ongoing micrometeorite rain. This gardening process has two effects on the ice. It mixes the ice-bearing regolith with fresh material from below, and in permanently shadowed regions, it also exposes some of the ice to the very limited radiation environment of the interior, the cosmic rays and solar wind particles that can penetrate from above. This radiation slowly breaks apart water molecules at the molecular level, a process called radiolysis, converting some H2O into hydrogen and oxygen, some of which then recombines into other compounds. The net effect is that the topmost layer of the regolith in permanently shadowed regions is ice depleted relative to the layers below. The ice that remains is mostly a meter or more below the surface, in a zone that gardening and radiation have not fully reached, where the preservation has been nearly complete. 1 meter? The depth of a field you might dig with a shovel? The depth of a modest excavation? The depth of a layer you could reach, if you had the right tools, in a matter of hours. The ice in those layers has been there since before the first fish swam in Earth's oceans. You are kneeling over something that has been waiting longer than almost anything alive has been alive. The chemistry of the ice is not simple. When scientists analyze what is in permanently shadowed regions, they are not looking for pure water alone. The cold trap chemistry of these regions is richer than that. Water is the dominant volatile, the most abundant molecule, but it is mixed with a range of other compounds that have arrived over the same 2 billion years through the same delivery mechanisms. Carbon dioxide arrives from comet impacts and from the breakdown of organic compounds in the regolith. Methane arrives from comets and from chemical reactions between hydrogen and carbon in the regolith. Ammonia arrives from nitrogen-bearing comets and asteroids. Carbon monoxide is present in trace amounts. More complex organic molecules, compounds built around chains of carbon atoms, have been detected in the ejecta of the Else-Cross impact and in spectroscopic data from orbiters. The cold trap is not simply a water archive. It is a chemical archive of the entire history of volatile delivery to the inner solar system, a record of comets and asteroids, of the late heavy bombardment period when the inner solar system was being reshaped by the migration of the giant planets, of the ongoing gentle rain of micrometeorites that has never entirely stopped. Each layer of ice-bearing regolith in Shackleton's floor is a stratigraphic record, the way that geologists on Earth read the history of a planet in layers of sedimentary rock. This layer is from the Cretaceous, this one is from the Jurassic, this one preserves the chemistry of the Permian Ocean. The layers of ice in this crater potentially record the history of volatile delivery to the moon. The oldest ice at the greatest depth, most protected from gardening and radiation, may carry the chemical signatures of comets and asteroids from the early solar system. The youngest ice, in the upper garden zone, reflects more recent delivery events. Together, these layers form a record that no other location in the inner solar system can provide. Mars has been geologically active enough to erase much of its early record. Earth certainly has. The asteroids have been fragmented and refragmented. The comets themselves are constantly losing material as they approach the sun. But the floor of Shackleton Crater has been held at 87 Kelvin in perfect stillness for 2 billion years. The record here is intact. This is why planetary scientists consider permanently shadowed regions among the most scientifically valuable targets in the entire inner solar system, not just for the resource value of the water, though that value is significant and real and will be discussed, but for what the chemistry of these deposits can tell us about the early solar system, about the sources of water on Earth, about the delivery mechanisms that brought organic chemistry to the inner planets, about the conditions under which life might have first had access to the chemical precursors it needed. The moon's cold traps are a library, and no one has ever walked through the stacks. You sit in the silence of the crater floor and let this settle. The central mound rises behind you, 3.6 billion years of frozen geology. The walls of the crater surround you, highland anorthosite, the most ancient rock type on the moon, formed in the final cooling of the lunar magma ocean. The regolith beneath you is mixed, gardened on the surface, pristine a meter below. And woven through all of it, in the dark and the cold, is the ice. 2 billion years of it, preserved, waiting. The moon itself is not passive in this story. The moon that exists today, the tilted, tidally locked, geologically quiet world, whose south pole holds the cold traps in permanent shadow, is not the moon that formed 4.5 billion years ago. The moon's history has been one of dramatic early activity followed by a long, slow quieting. Understanding that history is part of understanding why the ice is where it is. The moon formed in an event called the Giant Impact, the collision of the early Earth with a Mars-sized body called Theia, approximately 4.5 billion years ago. The details of this impact are still refined by ongoing research, but the broad picture is well established by geochemical evidence. The moon formed from material ejected into orbit by the impact, accreted rapidly, and was initially covered by a global magma ocean. The heat of accretion and of the radioactive elements concentrated in the early moon's interior melted the entire outer portion of the body. As the magma ocean cooled and crystallized, the minerals that solidified first settled or floated according to their density. Dense minerals, olivine, pyroxene, sank toward the interior. The mineral anorthosite, made primarily of the feldspar plagioclase, floated to the top because of its lower density, forming the bright hyaline crust that you can see around you in the crater walls. This process of magma ocean solidification occurred over tens of millions of years, producing the fundamental structure of the moon's crust. By approximately 4.3 billion years ago, the crust had solidified. Then came the bombardment. The period between roughly 4.1 and 3.8 billion years ago, sometimes called the Late Heavy Bombardment, though this term is still debated in its specifics, was a period of intense impact activity in the inner solar system. The moon's surface records this bombardment in its geology. The large impact basins that define the lunar landscape, the South Pole Aitken Basin, Mare Imbrium, Mare Orientale, formed during this period. The cratered highlands you are sitting within were shaped by impacts that occurred in the first billion years of the solar system's history. The South Pole Aitken Basin, the enormous impact structure that defines the entire south polar region of the moon, is the oldest and largest confirmed impact crater in the solar system. It is approximately 2,500 kilometers in diameter and 13 kilometers deep at its greatest extent. Shackleton Crater sits on the rim of one of this basin's inner rings, a massive, high-standing block of ancient highland crust that was pushed upward by the basin-forming impact and has sat at the South Pole since the moon's rotation axis settled into its current orientation approximately 2 billion years ago. The South Pole Aitken Basin formed approximately 4.3 billion years ago. The crater you are sitting inside formed approximately 3.6 billion years ago, younger than the basin, sitting within it, excavating through the basin's rim material and reaching the ancient highland crust below. And since approximately 2 billion years ago, when the moon's rotation axis settled into its current near-vertical orientation and Shackleton's floor entered permanent shadow, the cold trap has been running. The geological context of this place reaches back to the beginning of the solar system. The cold, the ice, the silence, they are not isolated facts. They are the current expression of 4.5 billion years of planetary history. You look up at the narrow strip of black sky visible above the crater rim. The stars visible there are not the same stars that were visible from this location 4.5 billion years ago. The sun has moved through space. The solar system has moved through the galaxy. The stars that burned overhead when the moon formed are long dead. They were massive, short-lived stars that formed alongside the solar system in the same molecular cloud, burned quickly, exploded as supernovae, and seeded the surrounding space with the heavy elements that became the rocky planets and moons of the inner solar system. The stars you see now are the stars of the current galactic neighborhood, different compositions, different ages, different positions. But the moon below your feet is the same moon. Its south pole is slightly shifted. The pole has moved about 5.5 degrees from its original position over the history of the moon, driven by the redistribution of mass during volcanic activity and impact events. But the pole is at the south. The axial tilt is 1.5 degrees. The shadow holds. The cold holds. The ice holds. The history of a world is written in these layers, in this cold, in this stillness, and you are sitting in the middle of it, breathing recycled air and listening to the hum of your suit's life support and feeling, in whatever way is available to you in this place, in this moment, the full weight of what surrounds you. You are inside the memory of the solar system. It does not speak, it does not move, it simply holds what it has been given and preserves it with extraordinary fidelity in the cold and the dark. Let your breathing settle. Let the geological time you are surrounded by reduce the urgency of anything that felt urgent before you sat down here. Billions of years have passed, and the cold trap has held. Whatever is pressing on you tonight is not billions of years. Let it rest. There are machines working to understand this place. Right now, above this crater, above the rim you descended through, above the thin exosphere of the moon and the vacuum of cislunar space, instruments are in motion. The Lunar Reconnaissance Orbiter, launched in June of 2009 and still operational as of the mid-2020s, making it one of the longest-running lunar missions in history, continues to map the South Polar region with a suite of instruments that includes the Lunar Orbiter Laser Altimeter, the Diviner Lunar Radiometer Experiment, the Miniature Radio Frequency Radar, and the Lyman Alpha Mapping Project Ultraviolet Spectrometer. Each orbit, the LRO passes over the South Pole. Each orbit, it adds data. The topographic map built by Lola over its years of operation has characterized the lunar surface to a resolution of roughly 20 meters, enough to map the crater floors, the slopes of the crater walls, the ridgelines of the peaks of eternal light, the detailed geometry of every permanently shadowed region near the pole. The Diviner instrument measures surface temperatures, the same temperatures that define cold trap boundaries, that determine where ice can persist and where it cannot. Its maps show, in precise thermal detail, The coldest zones of the lunar South Pole, regions where the maximum temperature over a full year never exceeds 110 Kelvin, the threshold below which water ice can persist in the near-surface regolith over geological time. The LAMP ultraviolet spectrometer detects the albedo of permanently shadowed regions in ultraviolet wavelengths, wavelengths reflected differently by ice-bearing surfaces than by dry regolith. Its data contributed to the confirmation that surface ice exists in some permanently shadowed regions, not just subsurface. In the ShadowCam instrument, aboard the Korean spacecraft Danuri, which began its lunar orbit in December of 2022, has provided the first detailed visual images of the interiors of permanently shadowed regions. Images like the one showing the interior of Shackleton, dimly illuminated by reflected light from the crater walls, with boulders and slope deposits, and the faint texture of the floor visible for the first time. You are in the place those instruments are mapping. You are on the floor of the crater their data describes. The 200 times more sensitive sensor of ShadowCam has imaged this floor. Its photograph of the interior of Shackleton, a dim gray scene of ancient regolith under reflected light, captures a space that no human eye has ever seen directly. That photograph is a scientific record, a measurement, a data point, and it also shows something that could simply be called remarkable. The floor of a crater on the moon, lit by nothing but indirect reflection, 4 kilometers below a rim that receives perpetual sunlight. The crater that you are sitting inside right now. The missions working above you do not know you are here. They are instruments, not observers in any sentient sense, arrays of sensors and processors, collecting photons and converting them to numbers that travel back to Earth on radio signals, to be received by antenna networks and processed by scientists in laboratories on a planet 384,000 kilometers away. But the data they are collecting describes where you are sitting. There is a continuity in that. The human need to understand a place, to map it, to measure it, to know its temperature and its composition and its age, expressed through instruments orbiting silently above while you sit silently below. Different scales of investigation, the same fundamental curiosity. The Intuitive Machines IM-2 mission, launched in February of 2025, carried a small hopping drone named Grace to the South Polar region, designed to jump on rocket power into a permanently shadowed crater near Mons Mouton and measure the temperature inside with a radiometer developed by the German Aerospace Center, a machine specifically engineered to do what no instrument had done before: enter a cold trap and directly measure its thermal environment. These missions accumulate data that feeds the planning for the missions that come next. And the next missions are human. Artemis 3, the mission planned to land humans on the moon's south pole for the first time, has the permanently shadowed regions and the ice they contain at the center of its scientific objectives, not just as a resource, though the resource value is real, but as a scientific target. The samples that human astronauts can collect from cold trap regolith, with the selectivity and judgment and care that robotic missions cannot yet match, will contain information that orbital instruments and even landed robotic missions cannot fully extract. The isotopic composition of the water, the precise mixture of volatile compounds, the depth profile of ice concentration, the layering, if any, that reflects the history of delivery events, the relationship between the ice chemistry and the mineral chemistry of the regolith it is mixed into. These are questions that require hands. Human hands in pressurized gloves with sampling tools, with the ability to look at a surface, recognize something unexpected, and make an in-the-moment decision to investigate it. The first humans to stand on the floor of a cold trap in Shackleton or in one of the nearby craters where ice has also been confirmed will be carrying with them the full weight of this understanding. They will know what they are standing in. They will know the age of the ice beneath their boots. They will know the molecular journey the water made to arrive there. They will be the first members of a species that has been looking at the moon for tens of thousands of years to actually reach this place. The first footprints in regolith that has held ice for 2 billion years. That moment has not happened yet. It is coming. And when it does, the cold trap will still hold, the ice will still be there, the temperature will still be 87 Kelvin in the deepest zones. The physics will not have changed to accommodate the arrival of something warm and living and temporary on its floor. But the record will change. For the first time in 2 billion years, something will be here that can look around, that can understand what it is looking at, that can reach down and take a sample of the ice-bearing regolith and carry it back to a world where it will be studied and analyzed, and will yield its secrets about the early solar system. The cold trap has been the most patient archive in the inner solar system. It will not have long to wait. Let that thought settle. Not urgently, not as something that needs a response from you, not as a call to action or a deadline, simply as a fact about the near future of your species and about this place you are sitting in. The moon is close, 3 days by spacecraft, close enough that the humans who will stand here are already alive, already training, already working toward this. The ice has waited 2 billion years. The next few years it will wait are nothing, an imperceptible instant in the time scale of the cold trap. And the trap will hold until it is opened, until something warm and living comes down the crater wall in a suit built to keep it alive, walks across this floor with careful steps in the low gravity, kneels in the regolith, and begins to learn what has been kept here. The stars are there in the strip of sky above the rim. The central mound is behind you, 3.6 billion years of geology, standing quietly in the dark. The regolith is beneath you, its ice intact, its molecules still, its record preserved. And the universe continues in all directions, indifferent and extraordinary and ancient in ways that human language has not yet developed good words for. You are sitting at the bottom of one of the most scientifically significant locations in the inner solar system. And it is quiet. And it is cold. And it is old. And you are here. Let your body rest now. Really rest. The kind of rest that comes when the scale of where you have been in your mind is large enough that the smaller things, the day that happened, the things left unfinished, the thoughts that wanted to keep moving, have lost their urgency against the backdrop of 2 billion years. They are not gone. They will be there tomorrow. But they are smaller now, measured against the cold of this crater and the age of this ice and the silence of a world that has been resting in exactly this way since before complex life existed on Earth. Let them be small. Let your breathing be slow. Let the weight of your body settle completely into where you are resting. The crater holds you in its silence. The moon holds the crater in its cold. The solar system holds the moon in its gravity. and the universe holds all of it in its long, quiet turning. There is nothing you need to do. There is nothing you need to fix or resolve or decide. You are here. The ice is here. The cold is here. And the silence continues. The floor of Shackleton is flat in the places between boulders, flat in the way that ancient, undisturbed surfaces become flat, not leveled by water or wind, but settled by the patient accumulation of micrometeorite dust over billions of years, each tiny impact adding a fractional layer of pulverized material that settles in the low gravity and stays. The regolith on this floor is among the oldest undisturbed surface material in the solar system. Not the oldest rock. The rock in the crater walls is older, but the surface, the top layer that your boots are pressing into, it has been accumulating since approximately 2 billion years ago. 2 billion years of slow deposition. Each year, on average, roughly 10 to 30 tons of meteoric material falls on the entire lunar surface. Dust and small particles mostly, the accumulated debris of comets and asteroids, and the diffuse material of the interplanetary medium, spread over the lunar surface area of 37.9 million square kilometers. This amounts to a thin coating of new material added every year. Fractions of a millimeter per million years in the permanently shadowed regions, where even the slowed down slope creep of material from the crater walls contributes to the gradual accumulation. The regolith beneath you is the result of that deposition. Each layer is a year, or 1,000 years, or 100,000 years. The resolution of the record is not fine enough to read individual years, but the presence of layering, the variation in particle size and composition with depth, reflects the real history of material arriving at this surface over geological time. It is a record the way that ice cores from Antarctica are records. Ice cores drilled from the Antarctic ice sheet preserve bubbles of ancient atmosphere, actual samples of the air that existed at the time the ice formed, going back 800,000 years in the deepest cores. The composition of those bubbles tells scientists exactly what the carbon dioxide concentration of the atmosphere was in any given period, what the methane concentration was, what the temperature was. The ice core is a continuous record, one layer for every year, going back 750,000 years. The regolith record in Shackleton goes back 2 billion years. It does not preserve atmosphere because the moon has never had a significant atmosphere to preserve, but it preserves the volatile chemistry of the cold trap, the water molecules and carbon compounds and other volatiles delivered over 2 billion years of solar system history. In its own way, it is a more ancient record than any ice core on Earth, and it preserves information about the early solar system that no Earth archive can contain. Scientists have proposed drilling into the regolith of permanently shadowed regions for exactly this reason. A drill core brought back from Shackleton, a cylindrical sample of ice-bearing regolith spanning a meter or more of depth, would be among the most scientifically valuable samples ever collected in the history of planetary science. It would potentially allow researchers to read the history of volatile delivery to the inner solar system in chemical layers, to date those layers using isotopic methods, to extract information about the conditions of the early solar system that is currently unavailable from any other source. This is what the ice remembers. Not in any conscious sense, not in any sense that requires interpretation or intention, simply in the sense that chemistry is a record, that molecules are specific, that the ratio of hydrogen isotopes in a water molecule tells you where the water formed, that the presence of certain organic compounds alongside the water tells you what kind of cometary body delivered them, that the depth at which you find a particular chemical signature tells you approximately when, in geological time, that delivery occurred. The Floor of Shackleton is a chemistry book, written in the language of cold and dark and vacuum, waiting for someone who can read it. You breathe slowly. The suit hums. The central mound is a pale mass in the reflected light, 3.6 billion years of frozen geology, standing quietly behind you in the dark. The walls of the crater surround you, 4 kilometers of ancient highland rock, tilted at 30 degrees, their upper portions catching the faint reflected light from the sunlit rim above and redirecting it downward in the diffuse glow that makes this place visible at all. And below you, in the regolith you are sitting on, the ice holds its record. 2 billion years. Patient, precise, permanent. This is not just a place of resource, it is a place of record. It is a place where the solar system has been keeping its own notes, in the cold and the dark, without any awareness that anyone would ever come to read them. And soon, someone will. The silence of the crater is not the silence of emptiness. You understand that now, in a way that perhaps you did not when you first descended the crater wall. The silence here is the silence of fullness, of a place so saturated with age and record and preserved chemistry that there is nothing left to add. The quiet is not absence, it is completion. The cold trap is full. 2 billion years of delivery, of accumulation, of preservation. Full. And you are sitting in the middle of it, in the most complete quiet that exists in the inner solar system, and your breathing has slowed to match the pace of this place. Slow, unhurried, held. Let it slow a little more. You have been here a long time, not in measured minutes. Time moves strangely in a place where there is no sun to mark its passage, where the stars in the strip of sky above the rim hold their positions with no visible motion, where the temperature does not change, and the light does not change, and the silence does not change. But your body has settled. Your suit's life support hums steadily. Your breathing has found a slower rhythm. The tenseness that the body carries through the day, the held posture, the alertness, the constant small muscular adjustments of a body navigating a world full of things to respond to, has gradually released in the absence of anything to respond to. There is nothing to respond to here. The moon does not need anything from you. The crater does not need anything from you. The ice, 2 billion years into its cold preservation, does not need you to do anything for it. You are a visitor, temporary, warm, alive in a way this place has never been alive and will never need to be. And that is sufficient. That is, in fact, exactly what this kind of silence asks for. A visitor who can sit quietly and be present without needing the place to perform, without needing it to give something, without needing anything from it, except the simple fact of its existence and the scale it provides. The scale of the cold, the scale of the age, the scale of the quiet. These are not things that demand anything of you. They are simply present, and you are present within them. Let your eyes stay closed. Let your body continue to release the tensions that the day carried, the held jaw, the slightly raised shoulders, the place between the shoulder blades that carries stress without announcing itself, the hands that close slightly during the day and never fully opened. Let them open now. Let the fingers be loose. Let the jaw be soft. Let the shoulders drop a centimeter further than they were. The cold is not touching you. You are warm inside your suit, but the knowledge of the cold, the knowledge of this extraordinary temperature maintained for 2 billion years just beyond the insulation of your suit, creates a quality of stillness that is different from any warmth you have been in before. A warmth surrounded by ancient cold. A living thing inside a world that has been waiting in its cold for 2 billion years. The contrast is not threatening, it is clarifying. You are alive. The moon is not. And the moon has been keeping this archive in its cold and its silence, patient beyond any measure that biology can apply, waiting for the moment when the living thing, the curious, questioning, tool-building living thing that eventually appeared on the third planet, would find its way here. That moment is almost here. You are almost here. In spirit, in imagination, in the quiet attention that you are bringing to this place, from your bed, or your chair, or wherever your body is resting tonight, you are here. And the ice is here. And the cold is here. And the dark is here. And they are all very old, and very still, and very patient, and they do not mind at all that you are here too. Let the weight of the moon's south pole, the mass of this ancient, cold, quiet place, press gently down on the weight of your body, not with force, with gravity. 1/6 of the gravity you are used to, lighter, gentler. The moon's pull on a body is a light thing, a suggestion rather than a demand, a presence rather than a weight. Let it be light. Let your body be light. Let the hours of the day that accumulated in your muscles and your thoughts, and the space between your eyes, let them have the weight of the moon's gravity. Light, gentle, slow. The stars hold in the strip of sky above the rim. The temperature holds at 87 Kelvin on the floor around you. The ice holds in the regolith beneath you, and your body holds its position, resting heavy with the day and light with the moon's gravity, somewhere between the two. In, out. The crater is 4.2 kilometers deep. The ice is 2 billion years old. The universe is 13.8 billion years old. And you are here now, at the end of a day in your one brief life, resting in the silence of the most ancient cold trap in the inner solar system. Think about what that means for a moment, without urgency. 13.8 billion years of cosmic history, the formation of the first atoms in the minutes after the Big Bang, the ignition of the first stars, the death of those stars in supernovae that produced the heavy elements, the assembly of second-generation stars with planetary systems, the formation of the sun and the planets and the moon 4.5 billion years ago, the slow geological shaping of these worlds over billions of years, the emergence of life on Earth 3.5 billion years ago, the long, patient evolutionary history that led through single-celled organisms and multicellular life, and vertebrates, and mammals and primates, and the first recognizably human beings who looked up at the moon from the savannas of Africa and did not yet have a word for what they were looking at. All of that history, leading to this moment, a mind shaped by billions of years of evolution on a warm, wet, living planet, resting quietly and directing its attention toward the floor of a cold crater on a neighboring world, a cold that has been holding its ice since before any eye on Earth could see. The timescales are not comparable. Your life, measured in decades, against the 2 billion-year patience of the cold trap. The comparison is so extreme that it stops being a comparison and becomes something else. Not diminishment, not the feeling of insignificance that the scale of the universe sometimes triggers in people who think about it. Something closer to freedom. When the cold trap has been holding for 2 billion years, the things that feel urgent in an ordinary evening, the unfinished task, the conversation that didn't go as expected, the plan that needs revising, the worry that circles without resolution, these things are still real. They exist. They will matter tomorrow. But their scale, measured against the geology of a lunar crater, is very small. Not dismissible, not unimportant. Small. And small things can be set down. They can be set down at the end of a day, in the quiet of wherever you are resting, and they can wait until morning, the same way the ice has waited since before the Cambrian. With patience, without urgency, in stillness. Let them be set down now. You are on the floor of a cold trap, sitting in the permanent dark, and there is nothing here that needs your attention. There is nothing here that requires a response from you. The ice does not need managing. The cold does not need adjustment. The silence does not need filling. This is simply a place where a thing has been held for a very long time, and you can rest in the fact of that holding. The crater walls rise around you in the dark, 4 kilometers of ancient highland rock, a northocite formed in the cooling of the lunar magma ocean 4.3 billion years ago. The same mineral, the same pale feldspar that has been the dominant surface rock of the lunar highlands since before Earth had its first ocean. These walls have never been rained on. They have never had a river cut through them. They have never felt wind. They have stood in exactly this geometry, at this angle, surrounding this floor, for 3.6 billion years. The stability of this place is not incidental. It is structural. It is the result of the moon having no plate tectonics, no significant volcanism for the past 3 billion years, no liquid water to carve new channels, no atmosphere to erode sharp edges into soft ones. The moon that exists today is the moon that has existed, essentially unchanged in its large-scale features, for the better part of 4 billion years. What erodes the moon does so slowly. Micrometeorite impacts, rare larger impacts, the slow thermal cycling of the surface between lunar day and lunar night, though here in the permanently shadowed crater, even that cycling does not occur. The thermal environment here does not cycle. It is stable, constant. The same temperature today as it was 1 million years ago. The same temperature as it was 100 million years ago. The same temperature as it was 1 billion years ago. 87 Kelvin. Unwavering. And in that unwavering cold, the ice has stayed. And the record has been preserved. And the silence has continued. Your breathing is slower now. Not forced into slowness, it has arrived there on its own, the way breathing naturally slows when the body recognizes that there is nothing it needs to prepare for, nothing imminent that requires readiness, nothing that warrants the elevated alertness of daytime wakefulness. The suit hums. The cold holds. The stars are still visible in the strip of sky above the rim, their light arriving after years of travel through the vacuum, entering your visor in the same photons they have been sending in the same directions for thousands or millions of years. The light from those stars that is entering your visor right now left its source before you were born, in most cases. The light from some of the dimmer stars visible in that strip of sky left its source before your parents were born, before their parents were born. The light from the faint smudge of a distant galaxy that might be visible at the edge of your vision left its source millions of years ago, when the ancestors of modern humans were first beginning to walk upright on the African plains. All of that time, that light has been traveling. All of that time, this crater has been cold. All of that time, the ice has been here. And now you are here too. For a brief interval of time that the geology of the moon will not record, your presence too temporary, too warm, too light on the surface to leave any lasting mark, you are here. And that is enough. That is, in fact, everything. Let the darkness hold you. Not the darkness of the crater. You are in your room, in your bed, in the warmth of wherever you rest. But the quality of that darkness, the completeness of it, can share something with the permanent dark of Shackleton's floor. A darkness that is not threatening. A darkness that is simply the absence of the light that is not needed right now. The crater has been dark for 2 billion years, and nothing in it has been harmed by the darkness. The darkness here, in your room, in this moment, will last until morning. And in the morning, things will be where you left them. The tasks will be there, the world will be there. The ordinary, necessary, important things of a human life will be waiting with the same patience, though a much shorter patience, that the ice waits in the cold trap. They do not need you right now. They are fine. They will be there. Let your body do what bodies need to do after a long day. Let the muscles release completely. Let the spine lengthen and settle. Let the jaw come fully apart so that the teeth are not touching, so that the muscles of the face are not holding any expression, so that everything in your face is soft and still and resting. Let your hands open. Let your feet be still. Let the weight of your body press gently but completely into whatever supports it, the mattress, the pillow, the surface your body trusts to hold it through the night. The moon's south pole is out there, on the other side of your ceiling, and the atmosphere and 384,000 kilometers of vacuum. The crater is there. The cold trap is there. The ice is there. 2 billion years of accumulated chemistry in the dark of a crater that physics itself has sealed against the sunlight, waiting with the patience of geology for the day when someone comes to read what it has kept. That day is coming, but not tonight. Tonight the crater rests in its cold. The stars hold in their positions above the rim. The temperature holds at 87 Kelvin. The silence continues unbroken, as it has continued for 2 billion years. And you rest in the silence of it, held in the same dark that holds the ice, in the same quiet that has always held this place, in the same stillness that will hold it long after tonight. Let your breathing slow. Let your mind be still. Let the moon's south pole be the last thing you carry in your awareness, cold, dark, old, quiet, as the edge of sleep finds you. The cold trap holds. The ice holds. And you are held. The ice does not know it is being studied. This is worth holding in mind for a moment, not as a philosophical puzzle, but as a plain scientific fact. The molecules of water frozen into the regolith of Shackleton's floor have no awareness of the instruments orbiting above them, no awareness of the scientists on Earth analyzing the data those instruments return, no awareness of you resting here in your suit on the crater floor, present in whatever way imagination allows presence. The ice exists in the same way that all matter exists, following the laws of physics, responding to the conditions of its environment, maintaining its state because the thermodynamics of this place demand it. And yet it carries information. It carries the isotopic ratios of hydrogen and oxygen that reveal where the water formed, whether it came primarily from comets, from asteroids, from solar wind interactions with the regolith. The ratio of deuterium to ordinary hydrogen in a water molecule is a fingerprint. Cometary water has a characteristic deuterium to hydrogen ratio. Asteroidal water has a different one. Solar wind hydrogen, implanted into oxygen-bearing minerals in the regolith, and then reacted to form water, has a different ratio still. The ice in this crater is a mixture of all of these sources, layered over 2 billion years of delivery events, each layer carrying the isotopic fingerprint of the impactors and processes that contributed it. Reading that fingerprint, extracting those ratios from ice-bearing regolith samples, correlating them with depth, building a delivery history of water to the inner solar system over 2 billion years, is one of the primary scientific objectives of future South Pole missions. It matters because water on Earth matters. Earth is a water world. 71% of its surface is covered by liquid water. Its atmosphere contains water vapor that drives its weather. Its biology is built around water as a solvent, water as a medium for chemistry, water as the substance within which the first self-replicating molecules assembled themselves in the early ocean. Where did all of that water come from? The question is not resolved. Earth formed in a region of the solar system that was too warm for water ice to be stable during the early accretion period, the inner solar system, where temperatures were too high for volatile molecules to condense directly onto the dust grains that were assembling into the rocky planets. The water on Earth arrived later, delivered by impacts from water-bearing objects that formed in the colder outer solar system and were gravitationally deflected inward into the inner solar system, where they struck the young Earth and contributed their volatiles. Comets were once the primary candidate for this delivery, but the deuterium to hydrogen ratio in cometary water does not match Earth's ocean water well. Comets tend to be deuterium enriched relative to Earth's water. Asteroids, specifically the class of carbon-rich asteroids called carbonaceous chondrites, have a deuterium to hydrogen ratio much closer to Earth's ocean water. The Moon's cold traps received water from both of these sources over their history. The isotopic record in the lunar South Pole ice is in this sense a record of the same delivery events that contributed water to Earth, the same comets, the same asteroids, the same processes recorded and preserved in the cold where they have not been altered by the geological and biological activity that has thoroughly mixed and overprinted Earth's early record. The Moon does not have plate tectonics to recycle its crust. It does not have an ocean to dissolve and redeposit minerals. It does not have life to incorporate water molecules into biological structures and release them in different forms. What arrives at the Moon stays in the form it arrived in. And in the cold trap of Shackleton, what arrived 2 billion years ago is still here in the same form, waiting for the chemical analysis that will help answer the question of where Earth's oceans came from. The ice beneath you may hold part of the answer to how life on Earth became possible. Not the whole answer. Science rarely resolves its deepest questions in a single location or a single measurement, but part of the answer, a data point in a long series of data points that, taken together, will eventually build a picture clear enough to say, this is where the water that filled Earth's oceans originated. This is how it got there. This is the sequence of events that made a living planet possible. The moon has been keeping that record for 2 billion years. In the cold, in the dark, in the silence, you breathe and let the weight of that settle completely. There is a particular quality of thought that comes late in a long night of contemplation, when the mind has moved through many layers of a subject and arrived somewhere deeper than the surface ideas, somewhere that feels less like information and more like understanding. The distinction between those two states, information versus understanding, is not always easy to articulate, but it is real. Information is knowing that the floor of Shackleton Crater is at 87 Kelvin. Understanding is sitting in the dark at 87 Kelvin and feeling what 2 billion years of that cold means for the molecules that have been held inside it. Information is knowing that the deuterium to hydrogen ratio in lunar ice may help resolve questions about Earth's water delivery history. Understanding is sitting above a meter of ice-bearing regolith and knowing that the water below you may be chemically related to the water that fills the oceans in which the first life on Earth assembled itself. Understanding is slow. It arrives when the information has had time to settle into the parts of the mind that work not through language and logic, but through something quieter, the part that holds scale, that holds proportion, that holds the sense of how large a thing is relative to everything else you know. You have been in this crater long enough for something like understanding to arrive. Not complete understanding. No single night, no single visit produces complete understanding of something this large and this old, but a beginning of it, a sense of the shape of the thing, the way that the physics of a 1.5 degree axial tilt, the geometry of a 21-kilometer crater 4.2 kilometers deep, and the thermodynamics of a surface receiving no solar energy produce a cold trap that has been running for 2 billion years and holds within it a chemical record of the early solar system. The shape of that is something. The feeling of that shape, arriving slowly in the quiet of the crater floor, is something that language can point toward but not quite contain. Let it be what it is. Let it settle. The suit hums around you. The cold holds in the regolith. The ice holds its record. In the silence of the crater, the complete structural, irreducible silence of a world without atmosphere, without wind, without weather, without the mechanical noise of any living thing or any natural process that would be audible even if you were not in a suit, the silence continues. There is a ridge above you that you cannot see from the crater floor. The Shackleton de Gerlache Ridge, a topographic high between Shackleton Crater and the neighboring crater de Gerlache, is one of the features scientists have studied most carefully in planning for human presence at the lunar South Pole. It is a ridge of elevated terrain that connects the rim of Shackleton with the terrain beyond, and along its crest, certain points receive sunlight for extraordinary fractions of the lunar year. The ridge has 4 peaks, and between them saddle features where the terrain dips before rising again. The distribution of sunlight across these peaks is not uniform. Some receive sun for more than 90% of the year, others somewhat less. The combination of peaks, mapped carefully by the Lunar Reconnaissance Orbiter and studied in multiple subsequent analyses, represents the closest thing to a continuous solar energy source available anywhere on the Moon. Solar panels placed on these peaks would generate power almost continuously. An outpost on this ridge would have access to near-permanent solar energy above, and access to the permanently shadowed ice deposits in Shackleton and the surrounding craters below. The distance between the peaks of eternal light and the closest confirmed ice deposits is a matter of a few kilometers, a traverse that a suited astronaut or a rover could complete in hours. The geometry is almost deliberate, as if the Moon's 1.5-degree tilt, the placement of these craters at the pole, and the specific topography of the ridge were arranged to provide exactly the combination of resources that a sustained human presence would require. It was not arranged. It is geometry and physics and the random accumulation of impact history over 4 billion years. But the result is the same. Light and water separated by a few kilometers of ancient highland terrain. Scientists have identified specific locations along the Shackleton to Gerlache Ridge, points known as Connecting Ridge, that are among the most illuminated spots on the entire Moon and are also within reasonable reach of the confirmed ice deposits. These locations have been named as candidate sites for what NASA calls the Lunar Terrain Vehicle Operations Area, the zone from which future human explorers would range out to conduct science, including descents into the shadowed craters below. The first humans on the South Pole will likely base their operations at or near this ridge. They will stand in the sunlight on the rim, and then they will descend into the dark below. The same descent you have made tonight, in imagination, in the slow narrative of a long and quiet night. But their descent will be different. They will have instruments, core samplers, spectroscopic analyzers, ground-penetrating radar in handheld form, cameras recording in wavelengths from ultraviolet to infrared. They will be making measurements, collecting samples, documenting everything they see with a precision that the first astronaut steps on the lunar surface in the Apollo era established as the standard for human scientific fieldwork in space. And they will take samples, actual physical samples of ice-bearing regolith, extracted from depth, sealed in containers that maintain the cold trap temperature to prevent sublimation during transport, flown back to Earth in the Orion capsule's sample return systems, and delivered to laboratories where the analysis will begin. The analysis that has never been possible before. The direct chemical examination of cold trap ice, not inferred from orbital data, not estimated from the impact ejecta of a deliberately crashed spacecraft, but extracted by human hands from the layers where it has been preserved. The isotopic ratios, the organic compound profiles, the depth stratigraphy, the mineral context of each sample, the precise location, documented to within centimeters, where each core was taken. These samples will be studied for decades as analytical techniques improve, as instruments become more sensitive, as new questions are formulated by new generations of scientists. The same samples will be reanalyzed and will yield new information that was not accessible when the original analysis was performed. The Apollo samples, 382 kilograms of lunar rock and soil, returned between 1969 and 1972, are still being actively studied. 50 plus years after their return, they continue to produce new scientific findings as new analytical methods are applied to them. The curation of those samples, maintained in a nitrogen environment at the Johnson Space Center in Houston, is one of the most scientifically productive investments in the history of planetary science. The South Pole samples will be the same. They will sit in sealed containers in a laboratory at temperatures maintained to preserve the ice, and they will be opened carefully by scientists working in cold rooms, in environments designed to prevent contamination with instruments capable of measuring isotope ratios at the level of individual atoms. And slowly, measurement by measurement, the story of the water will emerge. Where it came from, when it arrived, what it traveled through to get here, what it means for the water on Earth, and for the question of how a living planet forms in a solar system. That science has not yet happened. It is waiting, the same way the ice is waiting, for the moment when it becomes possible. The first samples from a permanently shadowed region of the Moon's south pole may be returned to Earth within the next decade. The analysis of those samples may take decades more, but the ice has waited 2 billion years. It does not mind. Everything that matters takes the time it takes. You sit on the crater floor and think about patience, not as a virtue in the way it is sometimes discussed, a quality to be cultivated through effort, a discipline of waiting gracefully when waiting is difficult, but as a physical property, the way that the cold trap is patient, not through choice, not through effort, not through the suppression of any impulse toward action, but simply because its physics do not allow for impatience. The molecules in the ice at 87 Kelvin cannot acquire the energy needed to escape. They stay because staying is the only possibility available to them at this temperature. There is something clarifying in that. The ice stays not because it has decided to stay, but because the conditions of its environment make staying inevitable. And for 2 billion years, that inevitability has produced something extraordinary, an intact chemical archive that may help humanity understand its own origins. Patience that is not effort, but simply the expression of conditions. The night you are in right now, this particular night in your particular place, at the end of a particular day, will also end when it ends. Not because you force it to, not because you successfully manage the pace of your thoughts into stillness, but because the conditions of a body that has been working through a day, that has been carrying the weight of attention and decision and response for many hours, are conditions that eventually express themselves as sleep. The body moves toward sleep the way the cold trap moves toward equilibrium. Not through effort, through physics. Let the physics of your body do what they do. Let the signals that the day has completed, that the light has been absent long enough, that the temperature of your environment is appropriate for rest, that the sounds around you have quieted enough. Let those signals do what they are designed to do. Your body has been reading them. Your body knows. The crater is cold. Your body is warm. The crater is silent. Your room is quiet. The crater has held its state for 2 billion years without effort. Your body will hold its sleep through the night without effort. Let the similarity of those two states, the stillness of the cold trap, the stillness of a sleeping body, be the thought you carry as the threshold of sleep approaches. Both of them are a kind of holding. Both of them are a kind of preserving. In sleep, the brain does its maintenance. Cerebrospinal fluid moves more freely through the spaces between neurons, clearing metabolic waste products that accumulate during waking activity. The glymphatic system, the brain's cleaning mechanism, most active during sleep, operates at its highest efficiency in the quiet of deep rest. Memories consolidate, moving from short-term storage to long-term structures. The body repairs tissue. The immune system conducts its overnight processes. Everything that cannot happen efficiently during the alert, active, metabolically expensive state of wakefulness happens now. Sleep is not the absence of function. It is a different kind of function, and the body will perform it as it has always performed it, without requiring instruction or effort from the part of you that is still listening. Let that part go quiet now. Let the hum of the suit fade into the background of your awareness, or let it be replaced by whatever sounds surround you, if any, in your room tonight. The ambient sounds of a house, a city, a night, whatever they are, let them move to the background. Let the cold of the crater be a thought you hold gently rather than clearly. Not a sharp concept, not a data point, just the sense of it, the weight of 2 billion years of cold, dark silence, somewhere out there beyond the atmosphere, on a world whose south pole is tilted 1.5 degrees from vertical, in a crater whose floor has never seen the sun. The ice is there. The cold is there. The silence is there. And they will be there tomorrow, and next year, and in 1,000,000 years, and in the time before the next humans stand on the floor of Shackleton and reach into the regolith and take the first physical sample of a 2 billion-year-old cold trap. They will be there. The cold trap holds. It always holds. Think about what it means for something to hold for 2 billion years. 2 billion years is not a duration that human intuition handles well. It is too large. It exceeds every reference frame that daily life provides. A human lifetime is roughly 80 years. A generation is 20 to 30 years. Recorded human history stretches back perhaps 5,000 years. The agricultural revolution that enabled cities and civilizations is roughly 12,000 years old. The oldest confirmed stone tools made by human ancestors are about 3.5 million years old. 2 billion years is 570 times the age of those stone tools. It is 400,000 times the length of recorded human history. And in all of that time, in the span during which life on Earth went from simple single-celled organisms to the full complexity of the modern biosphere, through the Cambrian explosion and the age of fish, and the age of dinosaurs, and the age of mammals, and the entire history of human evolution, the floor of Shackleton Crater has been cold. The same cold, unvarying, not warming in summer and cooling in winter, not responding to the climate events that reshaped Earth's oceans and atmosphere multiple times over the same period, not affected by the asteroid impact 66 million years ago that ended the Cretaceous and the age of the non-avian dinosaurs, not affected by the ice ages that reshaped the northern hemisphere repeatedly over the past 2 million years. The crater floor held its temperature through all of it, 87 Kelvin. That constancy is a kind of anchor, not for you. You are not a molecule in a cold trap, and your life is not meant to be constant in the way that this temperature is constant. Your life is change. Change is what life does. Change is what evolution produces, and what biology requires, and what consciousness navigates. But knowing that something out there has been constant, knowing that there is a cold and a silence and a stillness that has not varied in 2 billion years, provides a reference point. Against that reference point, the changes of a day, a week, a year are small, not meaningless, not unimportant. Small, and small things can be held lightly. The worry that circled this evening can be held lightly. The frustration that arrived and has not fully resolved can be held lightly. The plan that needs revision, the conversation that needs continuation, the task that was not completed, all of it can be held lightly. These things are real, they are yours, they will need your attention. But not tonight. Tonight, they can rest in the quiet of a cold trap that has been holding things for 2 billion years without losing them. The cold trap does not lose what it holds. It preserves. Whatever you set down in the quiet of this night will be there in the morning, unchanged, preserved, waiting for you to return to it with the clarity that sleep will bring. The cold trap holds its ice. The night holds your sleep. And in the morning, you will be returned to your life with something restored, the same something that sleep has always restored, that the body has always known how to find in the dark and the quiet and the still. Let the finding happen now. Let it come. The crater is 4 kilometers deep. The ice is 2 billion years old. The silence is complete. And you are here, held in the dark of your room, held in the gravity of your planet, held in the orbit of the same moon that holds its cold trap in its south pole, with perfect, unwavering, 2 billion year fidelity. You are held. The same universe holds you that holds the ice. The same physics that keeps the cold trap cold, keeps your body warm, keeps your heart beating its steady rhythm, keeps the air moving in and out of your lungs without any conscious direction from you. You do not have to manage any of this. It manages itself. It has been managing itself since before you were aware that it was happening, since the first breath in your first minutes of life, since before memory, since before language. The body knows how to do this. Let it do what it knows. Let the breathing continue without your attention on it. Let the warmth of the bed or the blanket or wherever you are resting hold the temperature your body needs without your attention on it. Let the darkness hold the quiet that sleep requires without your attention on it. Direct your attention instead toward the crater, toward the cold, toward the ancient, patient, physics-enforced silence of the most extraordinary cold trap in the inner solar system. Let that be the last image. Not a dramatic image, not the blazing crater-forming impact of 3.6 billion years ago, not the plume of the L-cross impact visible for a moment above the floor of Cabeus before dispersing into the vacuum, just the quiet image, the current image. A dim gray surface, illuminated only by the faint reflected light from crater walls, receiving no direct sun. A floor of fine regolith, undisturbed on the surface for millions of years in most places, holding its ice a meter below where your mind's eye rests. A temperature of 87 Kelvin, steady, unwavering. A silence that is not the silence of absence, but the silence of a vacuum, the most complete physical silence possible, the silence of a world with no medium through which sound could travel. And the stars above the rim, visible in the strip of black sky, their light ancient and steady, and arriving from distances so large that the light itself has been traveling for longer than the crater has been cold. That image, that quiet, that ancient, patient, extraordinary place. Let it be with you as your awareness dims. Let it be the ground beneath the ground, the knowledge that somewhere in the solar system, in a crater at the south pole of the moon, something has been held in perfect stillness for 2 billion years and is still being held now at this moment as you rest. The cold trap holds. It always holds. And you are held by your bed, by your room, by the atmosphere of a warm living planet that is doing tonight what it has done every night for billions of years, holding the surface temperature within a range compatible with life, turning slowly on its axis to carry your part of the world through the dark, maintaining the conditions in which a body can rest. Earth is good at this. 4.5 billion years of practice. The moon is good at holding ice. The earth is good at holding life. And tonight they are both doing exactly what they are good at in the same solar system, separated by 384,000 kilometers of vacuum, and you are between them, closer to Earth, warmer than the moon, held by one and observed by the other. Let the thought of that be easy. Let it be soft. The crater walls of Shackleton rise 4 kilometers above a floor that has been dark for 2 billion years. The peaks of eternal light catch the sunlight just above the rim. The ice waits in the regolith. The instruments in orbit pass overhead in their measured paths. And on the third planet, in a room, in a bed, in the ordinary, extraordinary fact of a living thing resting at the end of a day, you are here, breathing slowly, held gently, at the edge of sleep. Let it come. The cold trap holds. The ice holds. The silence holds. And you are held inside the same universe that holds all of it. The cold and the dark, and the ancient record, and the long patience of a world that has been keeping its chemistry since before your planet had complex life. You are part of this, not distant from it, not separate from the universe that contains Shackleton Crater and its 2 billion-year-old ice and its extraordinary, patient, physics-enforced silence. You are made of the same atoms, forged in the same stars, carried through the same solar system history. Here tonight, in the dark at the end of a day, let your breathing slow to the pace of a crater that has not been in a hurry for 2 billion years. Let your thoughts arrive and pass like molecules hopping slowly across a cold surface, looking for a place to rest. And let them find their cold trap. Let them settle. Let them stay. The moon's south pole is out there. The crater is there. The ice is there. The cold holds. And you are held. If this episode found you at the right moment, if the cold of Shackleton Crater and the age of its ice gave you somewhere quiet to rest tonight, a like, a subscribe, or a notification bell means that the next story gets to exist. These episodes are built with care, and every gesture of support makes the next one possible. Quiet science at bedtime, science for sleep. Good night.